IPA, or ImmunoPrecise Antibodies, is a biotherapeutic research company that brings industry-leading antibody discovery services and complex artificial intelligence technology together. And with me is CEO Dr. Jennifer Bath. Great to have you here.
Thank you.
So now, before we dive into the specifics of the company, just give me an overall explanation of the company and particularly how you're working with AI.
Okay, happy to, and thanks for having me. So IPA has actually been around for about 30 years. We develop novel therapeutics in large part for other companies. We've worked with over 700 companies to date, and typically those therapeutics are in the area of oncology and inflammatory disease, chronic and deadly diseases. Over the course of the past year, we've integrated our latest acquisition, a company called BioStrand, who has brought really innovative AI technologies, both patented discoveries and proprietary software, into our platform, and now we're actually accomplishing things that people have never accomplished in the biotherapeutic world, and applying those directly to discovering new drugs and bringing forward really the best candidates, leads, so that people can move into the clinic with better products.
Yeah, okay, I want to talk a little bit more about that, but you mentioned BioStrand.
Yes.
So this technology is the HYFT?
Yes, we call it the HIFT technology.
Technology, got it. Explain that, and why is that? How does that technology work?
Yeah, that's a great question. So the HIFT technology is actually named after one of the co-founders that actually discovered these. The HIFTs themselves are actually patterns, they're unique fingerprints that were discovered to exist in all biological data. And so they exist in DNA, they exist in RNA, they exist in protein, and they correlate to something very special. They're, in addition to being patterns, they actually correlate to very particular structures that are related to a function. And when we look at biotherapeutics, whether it's therapeutic antibodies or a vaccine, what we're always focused on is what is the actual function of that molecule. That actually determines what it does and how it will actually work. And that's been one of the biggest challenges in all of the life sciences, and an area that even as recent as a year ago, people thought we would never be able to solve. HIFT allows us to do that. It allows us to pull out the most critical information that is encoded and hidden in those patterns, and to be able to link that to the actual structure and function of the molecule.
Okay, and that, I guess, is where AI comes in, because you have a lot of that data that you've got, and that can kind of, I guess, sift through all of that and pull out important pieces of patterns and data that will help you?
That's exactly right. That's exactly right. We have actually taken all of those patterns, and they have been coded, and they have been indexed into what we call a HIFT index, much in the way that, for instance, Google indexes into the Google index. And what it means is that we can use any amount of data, our data, clients can come to us to use their data, and we put that into our software, and what happens is the HIFTs parse that information, pull out the most critical information, and do it instantaneously. So you immediately have access to, in what's called a knowledge graph, not only the 600 million HIFs that it's filtered through and the information that it connects it to, but also about 25 billion relations. So it's connecting it out there to not only sequence and structure, but also textual information, from articles to anything that might be written and substantiated and through peer review, bringing back just incredible amounts of information to your fingertips. And as I mentioned, it's instantaneous, and then also really importantly, it requires almost no energy to do it. We can actually move this through on simply CPUs because most of the data is actually irrelevant. What we're really focusing on is the patterns.
Okay, very interesting.
Yeah.
Can you give any examples of how you've seen this work and how maybe it's had a real-world practical application?
Yeah, absolutely. So we've been applying this in a number of different ways. One of the ways that we've been applying it is when people go through like the research portion of a campaign, when they're looking to discover a new drug, this oftentimes takes years of energy and tens of millions of dollars to get it to the point where it's ready to enter the clinic. And we've actually used these patterns to very, very early on determine which antibodies have particular characteristics of interest, which antibodies actually have the most human-like qualities, and that's very important because the more human a molecule is when it goes into either some modification periods or into a human, the less toxic it's likely to be. So it enables us to actually find the best drugs and the ones that are likely to be the least toxic very early on in the process. So we speed up that process of finding the leads that can be moved forward. And in addition to that, we save a lot of time. And a lot of money in being able to apply that.
Interesting. So where do you see this going? I mean, will this, and I can imagine when you combine this with quantum computing, you're going to be able to be even more powerful in finding this. How do you see the future of this?
So actually, there's a lot of different applications for this. Right now, we are getting requests, and we have actually signed a couple of agreements with a few companies, including one called Briacell, one called Astellas, who have actually asked us to take this technology and apply it to things, to the discovery of drugs that simply cannot be done in other realms today, cannot be done in a traditional setting. And we're fueling a lot of interest. We're getting a lot of interest from that particular area. I think that will be one area that we continue to apply, is looking at, for instance, being able to target the tumor microenvironment, where right now it's just a very difficult
Tumor micro, what is that exactly?
Yeah, so it's where when a tumor is growing, it oftentimes changes the environment around it. And things happen like the pH changes and drops significantly, and that makes it very difficult to build drugs that will attack the tumor and keep their shape when they actually reach the tumor, because the pH changes their structure and it changes their function. HIFs are very well suited to that type of application. But that's one of multiple areas we see this going into. Personalized medicine is a great interest for us, because we can actually understand the structure of the actual target. We can better align drugs to the structure that is not functioning properly any longer, ultimately with the goal of being able to personalize drugs for every patient, as opposed to selecting just whatever drug off the shelf has been approved in the clinic.
Right, okay. Absolutely fascinating. It's amazing the role technology is playing in health.
Yes, absolutely. More and more every day these days.
All right, Dr. Beth, thank you so much.
Thank you.
Brilliant.
They're my pleasure.